pancakes. So just imagine for a second that these circles represent pancakes with different numbers written on them. We could have any type of data here, but we're using numbers or integers as an example here. And one feature of pancakes, the real world pancakes, is that you can stack them on top of one another. So just imagine that this line here represents a plate. And once you have a plate, you can have pancakes stacked on top of one another. So you could have -1 at the bottom, and then you can put 3 on top of it. And then let's say this one 9, this pancake right here. And then at the top, you can put this one. And then you might say, okay, what if I wanna retrieve this pancake right here with the number 3 written on it? Then what you would need to do is you would need to take out this one first at the top, and then this next one, the 9 pancake, and then finally you can take out this one. So that's how pancakes in the real world work, and it's the same thing with the stack data structure. So a stack is a collection of data in which you can only add a piece of data at the top of this structure, or retrieve a piece of data from the top of this structure. So you aren't really able to retrieve data from any position, just like you could, for example, in an array. So another way to describe the same thing is that whatever piece of data you put in last will need to come out first. So in the current structure of these 3 pieces of data, the last piece of data that we put in is 9, so that needs to come out first. And that's sometimes referred to as last in, first out. Okay, so that's how a stack works, but how can we implement it? Well, one way to implement it is by using an array. So we have an array of 8 elements here, and we're going to try to represent this stack right here. To do that, the first thing we'll need to do is we'll need to have a pointer, or just an integer variable that's going to point to the last element that we put in this data structure. And let's say for now that the stack is empty, then there's no last element to point to, so we can initialize this variable to -1, or the index that would be here, but that doesn't exist. And this shows that this stack is empty. And now, what if we want to start putting in some piece of data here? For example, -1 here. Then what we can do is move the pointer here. Again, this is gonna always point to the last element that we put in this data structure. And then put -1 here. What if we want to put in 3 on top of -1? Then we can move the pointer again pointing to the last element that we put in, and then put 3 here. And then we can keep doing that. If we want to put 9 here, you can move the pointer here, or increment pointer by 1, and then put 9 here. And what if you want to remove this number right here, 9? To do that, all you need to do is you need to move the pointer back by 1, or decrement this variable by 1. You could do something with this number right here, either erase it or change it to something else, but it doesn't really matter, because in this data structure, we always know that the pointer always points to the number that's at the top of this structure. So the numbers following this pointer are not relevant. So we can keep going like this. If you want to put in 2 here, you can move the pointer back here, and then update this number right here with 2. And then if you want to put 9 again here, you can move the pointer by 1 and then put 9 here. And throughout this explanation, we saw a few key operations here. One is delete. Sometimes it's called pop. That's deleting or removing a number. from this data structure. And another one is add, and that's adding a number on top of this data structure. And with this particular implementation, you can implement both of them in O of 1 or in a constant amount of time. And that's assuming that the number of elements that we put in this data structure doesn't exceed the length of the array. And if it does, you will need to either throw an error or make a new array that's longer than the original array and transfer all the elements from the first array to the second array. And that would take some extra time. Anyway, that's it for a stack. Let's now take a look at a queue. The analogy I use to understand a queue is a bunch of people lining up in a line or in a queue. So let's say we have these people with some numbers assigned to them just for convenience, and they want to line up to do something. For example, to see this octopus for whatever reason. And this octopus is busy, so they need to line up. And with a queue, I think you already know how it works, but you can put people in the queue or in this line. And when the octopus is free, the person that's at the front of the queue can see the octopus and then go away. And then you can add more people in the queue or more numbers in the queue. And then the person or the number that's in front of the queue can see the octopus and then go away. So that's the idea of the queue data structure. And I think you can see that whatever number or whatever person that came in first will go out first too out of this data structure. And that's sometimes referred as first in, first out. Okay, and how can we implement this data structure? One way to implement it is with an array again. And this time we're going to have 2 pointers. The first one is going to point to whatever's at the front of the queue, or in this particular example, this number or this person right here. And we're going to put this one right here at 0 for now. And the second pointer is going to point to the space that's right after the last person or the last number in the queue. And for now, I'm going to put this at the same position as the first pointer at 0. And let's say that the queue is empty right now. Then we're going to make these pointers be initialized to both 0 right here. And we're going to implement this data structure so that whenever these 2 pointers point at the same thing, this queue is empty. Okay, now let's think about how we can represent a line of people with this particular implementation. So let's say that this person comes in the line first. Then we can put number 1 here and then move the second pointer right here. And if there's another person right after that, let's say 42, then we can put 42 here and then move the pointer here. Again, the first pointer will always be pointing at the first person in the queue or the front of the queue. And the second pointer will always be pointing at the space right after the last person or the last number in the queue. So let's keep going with this. If 13 comes in a line, we can put 13 here and then move the second pointer right here. And what if the octopus is free now and this person 1 sees the octopus and goes away? Then we can just move the first pointer over here. And we don't really have to do anything with this number right here, 1, because in this implementation, we'll know that the queue is only between these 2 pointers. So we can just keep going like that just to show you more examples. If -4 comes after that, we can put -4 here and then move the second pointer over here. If 0 comes after that, we can put 0 here and move the second pointer over here, or increment the second pointer by 1 and if 42 goes away, we can move the first pointer over here. Let me just keep going like this. And what if you have a situation like this now, where you have 3 people in the queue, 0, 1, and 42, and you want to add another person, -4 here. To do that, we can put -4 here, and then you would try to move the second pointer over here, but that's out of bound. To fix that, you can just move this pointer back here at 0 instead. So you can actually visualize this array like a circular array, where if you try to go out of bound, you just go back to 0. So let's just keep going like that. If we want to put 13 after that, you can put 13 here, and then move the second pointer by 1 over here. And it would work the same way for the first pointer too. If the first pointer keeps going to the right, and if it's about to go out of bound, instead of having it go out of bound, we can just bring it back to 0 right here. And another thing to note about this particular implementation is that you're only able to store at most n-1 elements in this data structure, assuming that the length of the array is n. To explain that, let's consider this situation where we have the second pointer right here, and we have some elements here, here, and here. If you try to add one more element right here, you would need to move the second pointer right here to the same position as the first pointer. But we've already said that in this particular implementation, if these 2 pointers point to the same thing, this queue is empty. But clearly it's not empty. And that's why we would need to stop here. And that's why we're only able to store n-1 elements where the length of the array is n. If you want to store more elements, you would need to either throw an error or create a new array that's longer than the original array, and then transfer all the elements to the new array. Anyway, in this implementation, we saw 2 key operations. One is removing an element or a person or a piece of data from the queue, and another one is adding a piece of data to the queue. Sometimes it's called dequeue and queue. And with this particular implementation, assuming that the number of elements doesn't exceed n-1, we can implement both of those things in O1 or in constant time. And that's it for a queue, but let's quickly discuss another data structure, and that's a deque or double-ended queue. It's a more generalized version of the queue data structure that we saw. And in this data structure deque, you're able to put data and remove data from either end of this queue. So you can remove this person right here, or you can remove this person right here. And you can add a person at the front of the queue or at the left side of the queue, or add this piece of data at the right side of the queue. And one way to implement this is similar to the implementation of the queue that we saw. So you can use a circular array still and have the same kind of structure. But in this new structure, we're able to remove data from either end and add data to either end too. So you would basically have functions that are called something like add left, add right, and remove right. Sometimes they're called pop left, pop right, or other names. But you get the idea. You should be able to implement all of those operations in O1 as well. Okay, so that's my introduction to these 3 data structures. But if you want to practice using these concepts, one of the resources I recommend is one of my business affiliates, algoexpert.io. This is my referral link, and this is my discount code, CSDojo. And there's actually an interesting problem that I found on this website for which you can use one of these concepts. So I want to give you a quick introduction to that problem. In this problem, you're given a string of different types of brackets regular brackets, square brackets, and curly brackets. You want to write a function that takes a string like this and returns true if the brackets are balanced and false if they're not. So what does it mean for these brackets to be balanced? To explain that, I think the best way to do that would be to give you a bunch of examples. This one is balanced because there are square brackets inside and regular brackets outside. This is not balanced, obviously. This is not balanced either because you're trying to close before you open. This one's not balanced. And this one is not balanced either because these two types of brackets are overlapping. Anyway, you should be able to solve this problem in O of n in time, where n is the length of the string and O of n in space as well. Anyway, sorry.